Day 36. Latent heat. The latent heat of a material is the amount of energy it takes per gram to change a material's state of matter. L sub F is the latent heat of fusion. The latent heat of fusion is the amount of energy it takes per gram to change a material from the solid to the liquid state or from the liquid to the solid state. L sub V is the latent heat of vaporization, and it's the amount of energy per gram to change a material from the liquid state to the gas state or from the gas state to the liquid state. Let's look at an example. Determine the amount of energy required to raise the temperature of 100 grams of ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. So all we're doing is changing the state of matter for water. We're going from the solid state, ice, to the liquid state, water. So that will require us to use delta Q is equal to m L sub F. We're going to use the latent heat of fusion. So we plug in the mass, 100 grams, and then we look at our data table for water. The latent heat of fusion for water is 333 joules per gram. So we put that in, 333 joules per gram. When we multiply, we get 33,300 joules. So if we had 100 grams of ice at 0 degrees Celsius, it would require 33,300 joules of energy in order to convert that ice from the solid state to the liquid state. Now, if we were to start out at 0 degrees Celsius liquid water and want to convert it to ice, that delta Q would be an mL sub F, but it would be negative because we are removing energy. So we would put that 100 grams and that 33 joules per gram and do it exactly the same, but we'd have to put that negative sign because we're removing energy. And then we would get that negative 33,300 joules of energy to go from the liquid state to the solid state. So to freeze water, we would have to remove that energy. What I'd like for you to notice is that all of these different materials have a different latent heat. But look how much larger the latent heat of vaporization is compared to the latent heat of fusion. The latent heat of vaporization is much larger than the latent heat of fusion. That means it requires a lot more energy to take something from the liquid state to the gas state than from the solid state to the liquid state. Notice for water, 333 joules per gram to go from the solid state to the liquid state. But if we take water from the liquid state and we want to go to the gas state, 2,260 joules for each gram of water. It takes that much energy. Let's do an example with this. Let's say we have 10 grams of ice at 0 degrees Celsius. So 10 grams of water in the solid state, and so it's at 0 degrees Celsius. And now let's say we want to take this 10 grams and we want to have water that's in the gas state at 100 degrees Celsius. And we want to ask ourselves, how much energy does that take? What is the delta Q? All right, so this is the question. So what do we have to do? Well, the first thing we have to do is we have to take the water from the solid state to the liquid state. Now, you may remember this picture that we made a couple days ago. We take solid ice, go to the melting point, heat it up, and now it's a liquid, heat it up some more, and now we go to the boiling point and heat it up some more, and then it goes to the vapor state. So we have the solid state, the liquid state, and the gas state. So what we're interested in right now is we're going to start right here in the solid state, and what we're going to do is we're going to heat this ice up to liquid water, and then we're going to heat it up some more, and then we're going to go to the boiling point, and now we're going to go into water vapor all the way to the gas state. So right there. So that's the amount of energy that we're looking for. We are trying to determine what this energy is, this delta Q. We want to see how much energy this is. So delta Q is going to be m L sub F, because we have to take this mass through the latent heat of fusion. Then what we're going to do is we're going to change the temperature of this mass by 100 degrees Celsius. And that's because the melting point is 0 degrees Celsius and the boiling point is 100 degrees Celsius. So we have to go through that temperature change. Then what we're going to do is we're going to take that mass and we're going to add more energy and go through the latent heat of vaporization. All right, so we have 3 steps to do. So we have our mass, which is 10 grams, and our latent heat of fusion. The latent heat of fusion is 333 joules per gram. Then we add the mass, 10 grams, the specific heat of water. If you forgot, it's on the previous day's data table, but it's 4.186 joules per gram degrees Celsius. Then what we have is a temperature change from 100 degrees Celsius minus the 0 degrees Celsius. So we have our final temperature minus our initial temperature. Then what we have to do is take that mass, that 10 grams, and multiply it by this latent heat of vaporization, 2260 joules per gram. So now what we have to do is get out our calculator. We're going through all those states of matter changes. So we have 10 multiplied by 333 plus 10, multiply that by 4.186, multiply that by 100. And then we're going to add 10 times 2260. And we get 30,116 joules. So if I have 10 grams of solid ice and I want to go to 10 grams of water vapor, it will require me to add 30,116 joules of energy. Now you may recall from a previous day's discussion that not only joules, but calories is an appropriate unit for energy. So let's convert this to calories. So we have a delta Q is equal to 30,116 joules. And there are 4.186 joules for every 1 calorie. So the joules will drop out, and we can calculate this in calories. So what we'll have is we'll have 30,116 divided by 4.186, and I get 7194 almost. 7194 calories. 7,194 calories. And you see, it's just that easy. So what you should do is get ready to do some problems, but before I let you go, what you need to make sure is if you have a specific material, you have to use the melting points, the boiling points, the latent heats of fusion, and that of vaporization for that specific material. So in the examples I've shown you, I've done this for water. But if we had a different material, they all have different melting points, they have different boiling points, and different latent heats. So make sure that you use the appropriate ones. The nice thing is that they all have the same type of graph, the solid, liquid, gas graph here. It's just that they have different values for the melting point and the boiling point. So make sure that you are aware of that. All right, well, good luck to you, and get started to do some of those homework problems and work on your quiz. Enjoy your day.